In this video, we will introduce our work BokehMe, when neural rendering meets classical rendering. Provided an all-in-focus image, a potentially imperfect disparity map, and some controlling parameters, our goal is to render high-resolution, realistic and adjustable bokeh images. Based on the observation that classical rendering methods suffer from artifacts at depth discontinuities, while neural rendering methods have difficulty simulating real and variant bokeh balls, we introduce a hybrid framework which combines a classical renderer and a neural renderer to make the best of the two worlds. For the classical renderer, we implement it by a scattering-based rendering method. The core idea of this method is scattering each pixel to its neighbor areas according to its blur radius. To determine the areas rendered incorrectly by this method, we conduct an error analysis between scattering-based rendering and real rendering on a virtual lens system. Here, we consider a simple scenario where only two objects exist in space. We finally derive four simplified rendering cases at depth discontinuities. Each subfigure represents that the rendered result of the center pixel is the integration of its neighbor pixels inside the transparent color areas. We then compute the color difference between the two rendered results. Take the first case as an example. Assuming the colors and the disparities of the two planes are constant, the color difference at each location is a function of two variables. The first variable alpha sub I can be represented as the ratio of the distance between the process pixel and depth boundary, and the maximum blur radius of the two planes. The second variable beta sub I can be represented as the ratio of the minimum and maximum blur radius of the two planes. Similarly, we can compute the color difference in the other three cases. According to the graphs of the color difference, we heuristically compute an error map, which is soft and tight, and basically covers the color difference in all cases. We also conduct a toy experiment to verify this. For convenience and efficiency, we serve the computed error map as pseudo-ground truth, and predict an error map by the neural renderer. Inside the neural renderer, we design two subnetworks, ARNet and IUNet, in order to handle the rendering at depth discontinuities and overcome the limitations of the blur range. Specifically, in ARNet, we first use an adaptive resizing layer to downsample all input images and scale the defocus values before feeding them into a CNN. The reason is that the actual signed defocus range is unlimited and may exceed the acceptable range of the network. Then, the error map is restored to the original resolution by bilinear upsampling, while the bokeh image is upsampled by IUNet. For IUNet, we propose an iterative guided upsampling mechanism to avoid the fuzziness and aliasing around in-focus areas during the upsampling. In each iteration, the original high-resolution input is adaptively resized, and the defocus values beyond the acceptable range of the CNN are clipped. Then, in guided upsampling module, we use the CNN upsampled results for small blur untrimmed areas, and use the bilinearly upsampled results for large blur trimmed areas. In this way, our framework can handle arbitrarily large blur sizes despite only training on images with small blur sizes. In this work, we also contribute a new bokeh dataset BLB, which is synthesized by Blender. The dataset contains 10 scenes, and each scene consists of an all-in-focus image, a disparity map and a stack of bokeh images with 5 blur amounts and 10 refocus disparities. In experiments, we evaluate the model on 3 datasets that were unseen during the training. The first one is our proposed BLB dataset. The second one is EBB 400, where we randomly sample 400 images from the EBB dataset and predict disparity maps by Midas. The last dataset IPB is captured by iPhone 12 portrait mode. We use this dataset for user study. From the quantitative results, our approach achieves the best performance compared with other SOTA methods. We also show a visual example of the IPB dataset. One can see that our model renders much more realistic bokeh effects at both object boundaries and out-of-focus areas. Note that iPhone 12 portrait mode cannot produce bokeh effects for objects in front of the focal plane. Finally, we show some synthesized animations with different controlling parameters to demonstrate the adjustability of our approach. For more details, please visit our website. Thank you for watching.